You know, if you've ever spent any time managing large-scale networks, you already know the absolute headache of traditional IP routing. I mean, at every single hop, a router has to dig deep into a packet, perform this complex super CPU-intensive Layer 3 lookup, and then calculate the best path forward. Look, it works, but at a massive scale, it is highly inefficient. So today, we're unpacking the overlay solution that literally transformed carrier networks, MPLS, or Multi-Protocol Label Switching. We're going to break down its architecture and mechanics so you can see exactly how it accelerates and secures modern data delivery. Let's get into it.
Here's the blueprint for this explainer. We're going to cover what MPLS actually is, the protocols behind it, the label stack, label forwarding tables, and finally, we'll walk through the entire forwarding process end to end.
All right, kicking things off with Section 1, what is MPLS? Let's hit the core concepts. To really wrap your head around MPLS, you kind of have to contrast it with what came before. Traditional IP routing requires every single router along a path to independently examine a packet's destination IP address, right? And then it has to consult this massive routing table. It's slow and it's super CPU intensive. Well, MPLS completely flips the script. It acts as an overlay technology. So instead of routing based on IP addresses, it directs data across the network based on really simple labels. It's basically this fast, streamlined label swapping overlay that lets the core network just skip all the heavy lifting of traditional routing. So what exactly is a label? Well, think of it as a highly efficient instruction manual attached right to your data. Technically speaking, it's a tiny 20-bit fixed-length field added directly to the packet header. Now, for the core routers, reading this little 20-bit label is vastly faster than trying to parse a bulky, full IP header. It essentially serves as a simple destination pointer, telling the router exactly what to do next. The router doesn't even need to know the final destination. It literally just needs to read the label. And because we're using these labels, we can create something really cool called a label switched path, or LSP. You can visualize an LSP as this highly controlled tunnel cut in right through the MPLS cloud. This isn't just some random route, okay? It is a very specific, predetermined path defined entirely by the sequence of label swaps happening at each router. This tunnel is a game changer because it allows service providers to guarantee performance characteristics, which, as we know, is absolutely vital for enterprise-grade networking. But you might be wondering, how do we decide which traffic gets which label in the first place? Well, that brings us to the Forwarding Equivalence Class, or FEC. An FEC is simply a grouping of different services or traffic types that require the exact same forwarding behavior. So if a bunch of packets are all heading to the same branch office and they need the same level of service, boom, they belong to the same FEC. The absolute crucial takeaway here is that the FEC is what actually determines which specific label gets pushed onto the packet the moment it enters the network. Moving right along to Section 2, MPLS protocols. Let's look at the label carrying components. We've got two main protocols at play here for actually distributing these labels. First up is LDP, the Label Distribution Protocol. Think of this as your everyday workhorse for basic, best-effort provisioning of the MPLS backbone itself. It just looks at the router's existing IP routing table to establish the path. But on the other side, we have RSVP, the Resource Reservation Protocol. Now, this one is much more demanding. RSVP is used when you absolutely need guaranteed quality of service. It literally requires the routers along the path to reserve bandwidth and resources before a single byte of data is even sent. So if you're running real-time applications, things like VoIP or video conferencing, RSVP is the protocol making sure your call doesn't drop. Now, regardless of which protocol is used to set up the path, the core mechanical action happening at every single intermediate router is incredibly elegant and fast. It's a simple three-step process. First, the router receives a packet with a stack of N labels. Second, it pops off that top label. Third, it swaps it by pushing a new local label onto the packet that directs it to the next hop in the path. Receive, pop, swap. That is literally it. No IP lookups, just rapid-fire label reading. All right, Section 3, the label stack. Let's understand these layers. Think about how a modern network actually runs multiple layers over a single physical cable. It's fascinating. We generally see three main types of stacked labels. The outermost layer is the transport label. This handles the tunneling and overlay across the core provider's MPLS backbone. Tucked right underneath that, you might have a VPN label, which provides the segmentation. This is what ensures customer A's traffic stays logically completely separate from customer B's, even when they're on the exact same wire. And finally, the innermost label is the service label, which handles flow control and quality of service for specific applications, like prioritizing voice traffic over standard data. Stacking these labels allows for just immense flexibility and privacy, all without needing separate physical infrastructures.
Which brings us to Section 4, Label Forwarding Tables and Processing Logic.
To pull all this off, a router relies on two distinct tables to figure out what to do. The LIB, or Label Information Base, is basically the learning table. It's used to distribute and learn all the possible labels across the network for a given IP destination or prefix. But here's the kicker. The router doesn't actually use the LIB to forward your data. Instead, the LIB's job is to populate the LFIB, the Label Forwarding Information Base. The LFIB is the primary operational table. So when a packet comes flying into the router at lightning speed, the router checks the LFIB so it knows instantly what active, pop, swap, or push action it needs to take.
Okay, final stretch. Section 5, the forwarding process. Let's walk through the step-by-step flow.
If you ever need to describe this process in an interview, this is exactly how you should break it down. The end-to-end journey of a packet through an MPLS cloud happens in 3 distinct phases, handled by different types of routers. Phase 1 happens at the ingress label edge router. Phase 2 takes place across all the intermediate routers in the core, and Phase 3 concludes at the egress label edge router. Let's walk through exactly what happens at each of these 3 checkpoints. Starting with Phase 1, you can think of the ingress router as the bouncer to the MPLS club. An entirely normal, unlabeled IP packet arrives at the door. The ingress router does all the heavy lifting here. It performs that one necessary initial IP lookup to determine the destination. Based on that destination, it identifies the correct forwarding equivalence class and the corresponding label-switched path. Once it's got that sorted, the router pushes a brand new transport label onto the packet's header. Boom! The packet is now officially inside the MPLS network. Now we enter Phase 2, the intermediate routers. And this is where MPLS just absolutely shines when it comes to speed. These core routers, they completely ignore the IP payload inside. They do not care what the ultimate destination is. They simply look at that top label, check their LFIB operational table, and perform their mechanical pop, swap, push. They pop off the incoming label, push on the new local label, and shoot it to the next router. This blazing fast swap repeats at every single hop across the core network. Finally, we reach Phase 3 at the egress router, basically the exit door. This router realizes, okay, this is the end of the line for the MPLS tunnel. It uses that final label to determine the actual next hop IP address, and then it strips away or pops off all remaining MPLS labels. The packet is now back to being a standard, everyday IP packet, and it gets forwarded on to the customer's local network using traditional Layer 3 IP routing rules. There's a quote from the source material that I think just brilliantly illustrates this entire concept. It says, MPLS acts like a conveyor belt. Each router only knows where to send the package next, guided by the label attached to the front of the box. And that hits the nail on the head, right? The intermediate routers don't need to open the box to read the contents, and they definitely don't need to calculate the ultimate route to the destination city. They just read the label, hand the box to the next guy in line, and move on. It is a masterpiece of networking efficiency. So that brings us to the end of our breakdown. But before we wrap up this explainer, I want to leave you with a thought. MPLS fundamentally proved that overlay technologies, abstracting the physical routing away from the logical path, can yield just massive benefits in speed, privacy, and control. So if MPLS is the highly efficient conveyor belt powering today's networks, what emerging overlay technologies might evolve or even replace this blueprint tomorrow? As you look into newer concepts like SD-WAN or segment routing, keep the mechanics of MPLS in the back of your mind, because honestly, its DNA is everywhere. Thanks for joining me on this explainer, and keep learning.